today, we are very excited to have George Williams with us. I think I saw his participation in the wave, so that was cool already. Already a win. But as the number of AI-powered devices rapidly grows, from satellites and drones to phones, appliances, and medical systems, we are entering an era where embedded machine intelligence is everywhere. George will walk us through how advances in model compression, chip architecture, and multi-agent systems are enabling AI to run efficiently at the edge, often in highly distributed and collaborative ways. So, please join me in welcoming George Williams.
Wow. That was an amazing introduction. Thank you. And I've never done a talk where the wave has preceded me giving the talk. So
we can do it after too.
Yeah, I feel like it's a lot of pressure. Will you do it during the talk too? All right, so yeah, thanks for inviting me to give this talk, The Next Frontier of Data Science at the Edge. And when I was, actually thinking about this talk and putting together the presentation, I ended up having like 3 or 4 hours of material because it's so rich and varied what's happening at the edge. I'm not going to do the 4-hour version. Here was actually my original agenda. And so, if this goes well, Victor, maybe you guys invite me back and we can do the more comprehensive talk. So what I'm going to actually talk about is agents in space. And it has, the essence of a lot of what I wanted to address in the comprehensive talk. So let's talk about agents in space. I've been really fortunate to do a lot of aerospace projects over my 20-year career in Silicon Valley. A lot of aerospace experts that I've met along the way. A lot of them are super good friends of mine. And like you guys, right? We've been noticing all of these great advances in AI, large language models, small language models, quantized language models, context models. A lot of hype that's we're noticing in this area, but there are a lot of practical use cases that are starting to appear. I was at your practicum workshop, and I think you guys have explored this space as well. And so, we thought, it was time to collaborate on a project that investigated the possibility of deploying this cutting-edge AI for deep space exploration. So I'll talk about our motivation and some experiments that we've done. So, usual suspects when we talk about deep space exploration. We've had various flavors of rovers that have been running around Mars. Just recently, a helicopter completed its first mission on the planet. And in a few years, we're going to have even more vehicles in remote space. So here, there's a rotorcraft we're going to launch to explore the moons of Saturn in another couple of years. So we've had a lot of success doing this, but there are a lot of challenges still, and I'll go through a few of them. These missions require a lot of continuous intervention, especially at times when the vehicle needs to deviate from its original plan. And this can happen quite a bit when you're doing deep space exploration. A rover needs to deviate from its original terrain path. Similarly, a helicopter might need to deviate from its flight plan. And low orbiting satellites, over the many decades we've deployed them, do need to deviate from their originally planned orbits. These vehicles don't have a knowledge base of the core science that's required for these missions, and instead rely on the specialists back here on Earth, the mission specialists and the scientists, to provide that scientific guidance. And because of all this, we can't really give these vehicles the ability to craft their own experiments, to selectively engage the scientific instruments that are on board these vehicles, and to, in general, give them the ability to make important mission next steps. So, right, you might be telling yourself, well, this has kind of worked for a few decades. Why do we need to change this? It sounds super complicated to figure out the kind of AI to deploy. And you're right, except right, we're still dealing with some fundamental challenges in deep space exploration. One of the challenges is pretty significant, and it has to do with the fundamental principle of physics. Here, I think this diagram depicts it nicely. We're looking at the relative orbit, and I show you Mars here, relative orbit of Mars and Earth around the sun. It takes 6 minutes of communication time for command to originate from the Earth, send it to a vehicle on Mars, and for verification to come back. And that's in the best case scenario. It takes 40 minutes, right, in the worst case scenario. So, this business of doing this remote control of science at these distances, right? It's slow, it's clunky, and it reduces the throughput of the science we can actually accomplish for these missions. This problem doesn't scale the further out you go into the solar system. Round-trip communication to moons on Saturn, that's about 3 to 4 hours. So imagine, right, sending a command, waiting 4 hours, right, for any kind of confirmation to come back. So essentially what we have is kind of this scenario here. We're just remote controlling a really expensive toy with a super large amount of latency in the response time. Of course, our dream, right, is the robot, right, scientist that we can deploy that understands the science of the environment it's being deployed into, and can craft its own experiments, report back on the novel science when it actually discovers something. There are a lot of really good outcomes to adding more autonomy for remote space exploration. Not only do we get higher throughput of science and discovery per mission, more coverage of the area in which the vehicle is deployed, more efficient use of the workforce back here on Earth, and in general, this will likely lower the cost to the barrier of entry for this kind of mission. More governments, more private commercial entities can get involved. So short of robot scientists, we wanted to, in this project, answer some fundamental questions on the relevance of cutting-edge AI for these kinds of very remote, very edge environments. And so we started this project, Marvis, Mission Autonomy in Remote Vehicles for Independent Science Surveillance. And we wanted to answer a few very basic questions. Can AI learn the science that's required for these missions? And probably more importantly, what kind of AI can we deploy for these missions, right? We're not talking about DeepSeek R3 at 700 million parameters. It's got to be something a bit more compact. This is very important. Can AI control its own navigation and more important than that, its own instruments? If we want the AI to craft its own plan and its own scientific experiments. If we have this, then we can possibly think about the AI making high-level decisions about mission next steps. We rely on the mission specialists and the scientists back on Earth for these high-level decisions. And this is super important. We're not trying to replace the experts back on Earth. We can't do that. I don't think the AI right now is good enough to do that. So if we're going to give it the ability to work on its own, it's going to get into situations where it's in over its skis and it's going to need to call back for help. So does the AI know enough to do that very important activity? A lot of these questions here are relevant to any kind of edge deployment when we're thinking about deploying AI, right, to smaller kinds of devices like this. And it's super relevant for this remote edge scenario that I'm talking about here. So a few months ago, we started out with a very basic proof of concept. So the proof of concept, we're not going to actually build anything. we want to understand some basic things about if the AI these days, right, that we have now can actually accomplish some of these, some of the things I mentioned in the previous slide. So we're not going to do a whole bunch of fancy curation of data just yet. We know we're going to have to do that. But does the AI we have available today, do the models today, do they have some scientific knowledge that we think might be relevant for these areas we want to explore into? We're going to choose a very simple agentic architecture. We're not going to do anything too fancy just yet. I'll talk about that in a second. Like I said, right, DeepSeek R3 is off the table. We need to consider something more compact, and we wanted to incorporate that into the early part of this project. And we're going to leverage simulation as much as possible. We don't want to build anything just yet until we can prove some basic things. So we started out with this quote-unquote simulation. We curated some images, and you can see here, right, the content that you see here is going to be very similar to the images that you're going to capture. We're using Mars again for this particular scenario and simulation. So, we have images of rocks, we have geological structures, sand, lots of sand, and we threw a few quirky ones in there just to see what the AI could do. I decided to choose in our first test two models, one from closed source and one from open source, GPT-4o mini, which I'm going to guess a lot of people have used here, and an open source model, in this case Gemma 3 at 4 billion parameters. So initially our bar was under 10 billion parameters, which seemed pretty reasonable. The rumor is GPT-4o mini comes well under that at 7 billion. They don't actually publish the details of the model, but from everything we read, it's very similar to a 7 billion parameter model. Gemma 3 is really interesting. I don't know if you guys have worked with any of the Gemma 3 models, but I've been super impressed with their performance. This particular flavor, it uses 4-bit weights. And so the on-disk size of this model is actually like 2.5 gigabytes. So it fits well under the budget that we assigned to it. And so I know a lot of you probably have used like post-quantization of models, and it's like, not so good when you post-quantize. They do some tricks to make up for that loss of accuracy by quantizing as they train, as they fine tune. And I noticed it's actually really impressive. So a couple models, they fit under our bench. There are a lot of other models we could have tried out there. And in fact, since this work, a lot more mobile edge models have appeared that look pretty impressive. Even Gemma 3 is now going to Gemma 3n, compressing even further. But we had to start somewhere. So the agentic flow is, like I said, we're going to do something just really straightforward to kick the tires. That you see here, right? These are cross-modal models, so you can prompt the image, prompt the model, sorry, with the image. And here, we're just going to ask the model for its scientific analysis of the scenario, the simulation image. The prompt engineering here is not too fancy. The system prompt is, we just give it its scenario. You're a rover, you're on Mars, a couple sentences, nothing super fancy there. And then that feeds into a triage agent. And so a triage agent, if you guys have used any of the swarm patterns, all it does is says, hey, I can take one of two paths. And so in this case, the Marvis either decides based on its scientific analysis if it wants to continue exploring or if it needs to call for help. So very simple, very straightforward. We know that when we need to deploy these kinds of things for real, the agentic architecture is going to get more involved, but we just want to prove some very simple concepts. I'll call it a few very important things about these leaf agents. They are tool and function calling agents, which means that in addition to the triage agent invoking a particular agent, one of these paths, it also spits out a piece of structured JSON. So this is important, right? Because we do have a fully agentic architecture, right, in this area. That agent is going to need to interface with an actual piece of equipment, right? Scientific instrument, right? So it needs to bridge. It needs to bridge the stochastic world of the model and the real world of actual devices that have an API or some kind of function calling ability. So we're just going to tease that out here, make sure it spits out some structured string. And this is really important. We want to make sure that it's getting this high-level sense of what to do, and we force it to give us a reason why it's choosing that path. So again, this is our very simple scenario, and I'd like to walk you through a couple of interesting examples from this test. So this is one of the simulation images. Where was that rock you saw? It's an interesting looking rock, actually. And we prompt the model with it, and again, right, we're asking its scientific analysis, given it's doing this exploration task. And so here's the response it gave. I'll give you guys just a second to read it. I think it's great to do this in this kind of crowd because you all have seen like model prompting live demos. If you want to actually see it working on my device, I can show it to you later. So it's kind of interesting. We didn't really know what to expect when we sort of started this project. I thought we wouldn't get too much, even from a small, compact geometry model. And as far as I can tell, this is a pretty plausible scientific response that it's giving for this scenario that we've set up. I'm not a geology expert. We ended up asking some experts a little later on, and I'll show you the results of that. So, pretty plausible scientific analysis. Let's see what path it takes. So it actually takes the path to continue exploring. I'll give you a second to read it. Again, it's a pretty plausible scientific explanation for why it's chosen to go down this path. And I think it's really interesting, given this compact model, it's linked the scientific analysis it did previously with its rationale for why it wants to go down this particular path. So, very encouraging results. We're just vibe checking initially. We talked to some experts later. Let me show you one more example. Probably noticed this one in our simulation set. We want to we chose a few examples like this. I like this because we wanted to understand a few things about the model, right? Does it understand kind of anomalous kind of scenario, and what will it do if it detects this? So its scientific analysis it's pretty cool, right? It does some really good object recognition of the image. Right? It's found the heel impression. It's given us some scientific subtleties around the imprint. This indicates relatively recent deposition. Again, right? It was good to see this. It was totally unexpected, the kind of result you would get again from a really small model, but we were super impressed. And I'll talk a little bit more about the expert analysis that we did. What it does, you kind of expected this. It decides to call for help. And this is kind of what we're trying to coax from the model, right? Do you know enough to sort of say, I don't know enough, and I need to engage the humans back on Earth? And so this was really important for us to get to because there are a lot of very high-level, important risk and reward decisions, right? So this AI is going to need to make on its own in these remote environments. We want to make sure it knows enough to know it's in over its skis. And I'll just I'll say something about the prompt engineering. If you want to look at the prompts later, I'll show you. We didn't actually in the system prompt say if you detect something that is like biological activity, or if you detect something that indicates water or something like that. We didn't instruct it to do that. We just said, hey, if you detect something you are not expected to see, that's one reason why you should call the scientists back at home. So, a lot of good results from the vibe checking we did on these images, these scenarios. But does it hold up to expert scrutiny? So, how we decided to do this, there are a lot of options out there to sort of do assessment of how the responses of these models. For us, given we have this rich network of experts in our network, a lot of them that actually have planned these kinds of missions, we thought we would engage our network of really smart engineers and scientists to see what they thought. And so we created a survey, reached out to our network. We identified many of them that actually have experience doing these kinds of planning for and implementing these kinds of missions. 40% of them in our survey. And we gave them the exact responses from Marvis. We gave them all the simulations, showed them like the system prompt, and had them rate their impression of the AI's responses. We gave them a simple 5-point rating scale initially. And so here are the results of our most extensive survey, the non-expert evaluation. I'll show you the expert in a second. And so we did pretty good to great, pushing great on average for all of the responses. So the expert, I'll show here, we go down by a point. I wasn't terribly surprised, right? The experts are going to have a higher bar for what they think it should be a good response. I expected it in the evaluation of the model's scientific evaluation of the image. It's correlated, interestingly enough, to the decision. I wasn't expecting that. But this is why you do these surveys, to get past your own biases. So we thought this was, again, right, super encouraging. We're in the positive territory for both the smart non-experts and the deeply experienced experts. And I should note the two examples I showed you before, those were from the Gemma model. You might be asking, well, what's the difference between the Gemma model and the O4 mini model? We didn't find any big difference between the two models. And I actually looked at the responses, and they both had, at least with my vibe check, they both had a similar kind of quality. You can say a lot of things about why this is. There's a rumor the open source models have caught up with the closed source models. And for me, this sort of is evidence that that's really starting to happen. Can I say questions? Okay, great. So this sort of model evaluation that we did in these scenarios, right? We're trying to understand a few things, right? Right? Does the scientific analysis that these models inherently have, right? Are they doing something that resembles science? And also, do these models have the capability to make these sort of high-level decisions about mission next steps? And that was really what we were trying to do with this very simple scenario. So a lot of this stuff that I talked to you about, we were going for some seed funding actually for this project. And so we had some milestones that we had to actually hit on. So this was one of them. It was very encouraging to report. But even more important to this, right, was also an analysis of how practical it is to deploy this model, right, for this remote edge scenario. So that was the second part I will talk about here. So in terms of, right, when we're talking about deploying advanced algorithms or compute for these missions, here's a good example. This is the helicopter that was deployed in the last few years for Mars. And I circled, when we're talking about advanced compute, power efficiency, I circled the two most important things. It's got a solar panel and it's got a battery. And in these missions, it spends part of its time, a significant part of its time in many cases, charging the battery. And then the rest of the time, depleting that battery in order to execute parts of the mission and perform these various tasks. And so it has to, there are various parts of the system that are important that the battery needs to power. And so these missions have very tight budgets on weight, on the kind of compute you can deploy, on the kind of batteries they have, the power efficiency of batteries, and it's important to have power efficient algorithms, in our case, models, which is why initially, right, we were looking at compact types of models. So we looked at lots of kinds of hardware for this. NVIDIA makes an edge chip. There are a lot of startup companies these days that are doing edge chips. We settled initially on the Qualcomm chip and one of their most recent chips. Here I just show a schematic of what's in one of the most recent Qualcomm chips, the Snapdragon. And if you don't know Qualcomm, I know you guys know. If you don't know Qualcomm, right, they have this very rich history of creating very powerful, efficient chips for the mobile kinds of environments. Laptops, phones, lots of industrial IoT edge processors that they go into. So in addition to being generous sponsors of our project, we did evaluate lots of different options. And for a lot of reasons, we chose this particular chip. There's a lot of things going on in a typical SoC, like a chip these days. I'll highlight the most important thing for us, which is true of a lot of chips that are being created, is that there's now special silicon in the chip just for executing models. This hasn't always been the case. For a while, right, some of these chips started including GPUs, and models were running them with GPUs, but now there's just dedicated transistors for any chip. So Qualcomm's making I think they're coming out with a new set of laptops, or just running Windows using this chip. And I think Intel has got their own version of NPU. I don't know if you guys might have newer laptops that have this silicon. So this is really the trend for all edge chips, is dedicated parts of the chip for just running models. And a lot of this development has happened, when I was at Apple several years ago, I got to kick the tires on the first Apple Girl engine, which is a few years ago. But now the rest of the chip market has really caught up. And this is how they're designing this stuff. So, it's great, right? We have this dedicated area on a chip for running models. Does that mean it's power efficient? And so what we decided to do is to actually do measurements to understand how power efficient it is to run a model the size of Gemma, and just to measure how much battery power does it consume. So we did an experiment. We created a program that just does continuous inference on the model here. We're just running the same prompt on this model on the chip, and we're targeting in the left. We're targeting the CPU because the CPU is actually still pretty powerful and it can run these models. And on the right, the NPU. And we want to understand a few things about the performance. Power efficiency is important, but as you guys know, right, you compress things down and you still need sort of other things that other metrics are very important too. We basically, these are on C++, on, if you guys know Onyx, right? Onyx runtime. We made our own C++ program. So really, right, it's not even right the below the Python. We made really efficient programs to compare CPU versus NPU. Power efficiency being right now the most important thing that we care about. And here are the results. We're running this continuous inference targeting those areas of the chip, CPU and NPU. And you can see here that we get pretty much twice as much battery efficiency from actually running the model on the NPU. I actually didn't expect it to be this power efficient, but makes sense, right? If you're actually designing math operations, right, for neural networks in particular, it makes sense that it's going to be more efficient, right, than a general CPU, which is meant to handle general kinds of work. So it was really surprising to see this kind of performance. And when you're working with edge projects in general, as you will likely be, these are not. It's not unlike the measurements you're gonna do right when you start to target edge chips. So you not only care about model performance and token rate and model accuracy and these things, but you're gonna be worried, right? Oh, if I run my algorithm, is it gonna last like 2 minutes or is it gonna last 3 hours? For us, it's super important to actually characterize the power performance and power efficiency. So, right on that note, you might be wondering, that's great for power, but how well does it perform for some other things? You want good token rate. So I've overlaid the token rate that we measure here for both of those workloads. And we get slightly better token rate even on NP operating in this low power regime. Other things I know you guys are interested in, right? Model accuracy, right? If it's just spitting out random tokens, that's not useful. But we're in the progress of doing some more measurements. But this was super encouraging to see this kind of power efficiency for this chip. So we feel like we made a pretty good decision about that. But these things, right? You're going to have to measure these things once you start to deploy at the edge. This is really important stuff to measure. On that note, right? Again, right? This is sort of the model, sort of selfish, centric view of using the battery and the compute. A lot of other things have to happen that use the battery on these systems. It needs to power the system, right, for navigation. There are tons of instruments, right? And so, in addition to, when you guys do these kinds of things, measuring the power performance of your algorithm on a chip, right? You're going to also have to measure overall system performance as well, and that's even more important, right, for these kinds of devices. But it's also important for any application, right? Because there's different parts of the algorithm that are going to run on different parts of the system. So system performance is really, really important. So we thought this was really encouraging. We met a couple milestones, right, for our seed funding event. Yay. And so we decided, and so the seed funding is going to actually, now we're going to move forward on building an actual prototype, right? POC proved a few of the things we needed to prove, which is fantastic. So this is what we're building right now. You can see there, we just started planning this, so we're definitely open to ideas. There are a lot of rover projects out there that are openly available and open source. You can get 3D print plans to do print a rover. There's even one that emulates one of the earlier JPL rovers. That's it's completely free. There are plenty of flavors of drones out there, and so the idea. So we're being very ambitious, right? Is we're going to have a agentic-based swarm where the rover and the drone actually team up to sort of do some scientific investigation and then figure out collaboratively what kind of scientific instruments to engage. The scientific instruments we're going for now are a hugging face little robot, reinforcement learning arm for sample collection, a portable GC, a portable microscope, and a portable mass spectrometer. We're actually starting to create the 3D simulations that we're going to evaluate a lot of the models on. Right, in a POC, we were just taking off the shelf Gemma just to see what it would do. We know we're going to have to train and fine tune and possibly reinforcement learn some models for a lot of the use cases. For example, these models don't understand standard mass spectroscopy data, we imagine. So there's going to be some specialized model training that we do, and a lot of that we can prove that out as in a digital twin, in a 3D simulation. So you can consider that sort of synthetic data, which is like all the rage in various domains. Here, it's a very 3D. Some of the simulation environments we're going to create. Once we have a prototype in 6 months to a year, we'll deploy to one of the planet surface simulation environments. There are a few located here. in the US we have access to, and also a few in Europe. As far as like what we're going to have it do and the scientific sort of experiments, this is like very recently. This is as far as we thought, right? So, but that's the general plan for getting to the next level of this project. So, I'll sort of highlight the most important aspect of this project, right? We're talking about autonomy and science autonomy, and so a lot of great projects on autonomous navigation for drones and for rovers. We're going to use a lot of off-the-shelf stuff, right, to do, and a lot of challenges still with autonomous navigation, right? But our project is really about high-level decisions about science, and so I circled perhaps the most important aspects of this project, right? This scientific instruments, because we would like to know, right, with real scientific instruments, right, can the AI actually engage this instrumentation and create its own exploration trajectories and experiments on their own? That's the most important part of this project. All right, final slide here. A lot of dots we haven't connected yet. This happens with a lot of crazy ideas at the start, right? You try to prove out certain concepts, and you sort of incrementally move forward to the next stage. But what happens is you end up creating more questions as you start to answer questions by more pop up. I mentioned a few of them, right? There's this interplay of model evaluation and model compression. We're getting to a point now where aggressive compression down to int3, to ternary weights, to binary weights, it's becoming a reality. It used to be, I played with a lot of these algorithms very early on. It's like, it was cute, but it was like not too accurate. But a lot of the work in recovering accuracy after you aggressively compress is starting to pan out. And we're starting to see credible models that can get compressed down to ternary weights, right? And in addition to that, as much as we love Qualcomm and we love their hardware and their roadmap for how they want to support Gen AI in edge environments, there's a lot of other competitors out there that are actually developing silicon, and I worked on one of them, for not baking in the processing of data types down to the chip. So most of the chips you use today, right, have float 32, float 16, integer 16, integer 8, in 4, they're baked in as a data type down to the chip, the transistor. So there are new chips coming out that don't have a data type baked in. Like you program your own data type. And you can do a lot of really interesting things in the mixed precision world if you can program at a microcode level the math for mixed precision. So a lot of this new chip technology for the edge that's coming out. And so, right, in addition to the plethora of models that we have out there, there's a lot of variety in the compute graph that underlies the model and how you execute that compute graph in hardware. That's going to change quickly it's already happening now. It's going to change quickly over the next year or two. But, right, you still need to evaluate. You need to train some of these models. You need to compress. You need to train in a quantized aware way, and that's still pretty tricky these days. And so, constant evaluation of the models as you compress is really important. Model training, like I said, right, the off-the-shelf models are not going to be able to deal with a lot of data that we're getting from these scientific instruments, and so we're going to need to figure out what kind of model training we need to do, right? Is it just fine-tuning? Is it just sort of trying to get longer context so you can do few-shot learning? We're not sure just yet. But when you're thinking about an edge environment, you can't do all the things, right? There are going to be some things that are going to be more apparent for these compact environments. Off-the-shelf models, I didn't talk about hallucination, right? Science. You want to deploy a model that claims to understand science and make sure it doesn't hallucinate. Yeah, definitely. And the traditional way, right, is have some kind of data set which mitigates the hallucination we know we're going to need a database, right, in order for the thing to have memory. It's going to have to remember. The exploration that was done previously, that needs to be compact. What does that look like? We're big on binary vectors these days, right? We can actually take a vector of floating point vectors and compress it down to binary and still retain a lot of the semantic meaning. So that will likely factor heavily into this. And everything I talk about here is going to be relevant for any edge kind of deployment. So maybe less relevant for a standard edge deployment. You have a very thin pipe of data to another planet or another moon. So it's not like you can sort of say, hey, I want to update the LoRa weights for this model. That might take a long time. That might take weeks, right, to do one update. So on-device learning is going to be key. These are quantized devices, right? How do you learn in a quantized environment? There is Q-LoRa, quantized LoRa, these kinds of things. So and reinforcement is resurging again, and that's another area where we want to explore, is that we're going to have on-device learning. It's going to have to be adaptive. That's an important aspect to a lot of edge environments. I showed you a very cute, agentic architecture with 3 agents, but once you start to think about a full system, you start to incorporate a lot more agents. One of the scientists, one of the experts in the survey said, "Oh, hey, where's your safety agent?" And this was echoed by everyone actually who has done these missions. Is that very important thing is safety? Is can the AI figure out if what it wants to do is going to be safe? This is a very important aspect of the project. We didn't think about it initially, but it kind of makes sense. Safety is important. And I talk about merging control systems. You notice the token rate, right? Eight tokens per second. It's not horrible. It's not great. And so when you think about existing systems that need to make decisions a lot faster, like navigation systems, they operate under a very tight kind of control feedback loop. You're not going to be able to actually have a system like that that's fully agentic, at 8 tokens per second. So a lot of the agentic part of this needs to actually merge with existing kinds of systems that are rock solid, that are tested, that have certain known characteristics. And this is going to be true of any project these days that is going agentic. It does need to interact with parts of the world that aren't agentic. That merging can be challenging. One of the experts finally said, "Oh, what about cybersecurity?" And we're like, well, who's going to be hacking an agentically controlled rover on the moons of Saturn? But there's an AI race happening right now. There's still a space race, and there are cases where there have been attempts to hack these kinds of systems, by competing entities. And so, one of the potential funders actually told us, yeah, you're going to need to think about cybersecurity. You're going to need to protect your supply chain, not only just the silicon, And you tend to source even this Qualcomm Edge device here, it probably sources from 4 different countries in order to make this device. So how do you protect that supply chain, to ensure that the device you're deploying, which you can't update, which you can't service, especially in remote scenarios, how do you protect that before you deploy? There are various ways to do this. There's watermarking things you can do in chips and silicon to identify them uniquely, to verify the chain, the governance chain. And that apparently is, we didn't know, that apparently is really important even in these sort of deep space exploration studies. I will say that agentic security in general is a big topic these days. I think I read recently that the cybersecurity industry is now admitting that AI right now is the largest security challenge that it's ever seen since the beginning of cybersecurity. And I believe that the attack surface is changing quickly for distributed systems, because now we have stochastic things talking to each other. and affecting how overall decisions are being made. Probably less relevant here, probably more relevant for a lot of the edge things that you guys would be working on, right? When you put these kinds of models, when you have agents talking to each other at the edge. But I think even in this project here, we have to address security, and that's just going to be, I think, a constant in edge deployments going forward. I think I went over lots of time. Thank you for giving me the time. This project is, right, it has some interesting aspects to it if you want to learn more. There's one of our earlier surveys that we did that you can participate in. You can see all the simulation and scenarios and actually provide your input if that's of interest. And yeah, there's likely to, now that it's like you get seed funding in order to make something, right? Not a whole lot, but it's, these things can snowball in the right way. And that's all I have. And thanks for letting me do the short version of this talk. Hopefully I chose the right topic. I think it has a lot of relevance to general edge. This is obviously the extreme edge, but I think a lot of projects have a lot of similarity to a lot of the decisions we have to sort of, a lot of things we need to think about and the decisions we needed to make with balancing model accuracy, model type, capability, and how it can get deployed practically. Questions? I think Victor, you also had a question.
Yeah, I'll go after. I'll
sit
in the best for last.
Hi, George. Thank you for your talk and your time. My name's Georgia. I had a couple questions about some of the feasibility aspects of the project, if that's okay. I was looking online during your presentation. I think cost is somewhere between 20 to 200,000 per kilogram sending to Mars.
Yep.
And when we're thinking about having like larger models on the edge there, I mean, the rover's tech specs, I think, for like 2 gigabytes of total system memory.
Yeah.
And those are just like much simpler like design loops because of the redundancy needed, because it can't break while it's out there.
Yep.
How is that balanced against like the time saved from like waiting for messages and relays for like missions and stuff like that? Like, where's the feasibility there? Like, how is it cheaper, right? Like, that's my question.
Yeah. We get asked this when we present. We've been fortunate enough to work with a lot of folks, like I mentioned, who have planned these missions. There is a lot of expense, and we didn't know this. There is a lot of expense maintaining the human workforce on the ground. We interviewed some of them. One of them, off the record, said there were some days when I was spending just 80% of my time just waiting, right, for stuff to happen. So, and the workforce that you need to have are very specialized. And so there's a lot of efficiency that can happen with the workforce. For some missions, that workforce can, for the ongoing costs, not the initial capital expense, right? Creating the vehicle, deploying it, you're kind of done with the capital expense. The ongoing costs are significant for an entire mission. That can be between 20 to, I think we have in that pitch deck, like to 60% of the ongoing mission costs. So, and that's just using the workforce more efficiently. And just to go back to we're not replacing these people, right? A lot of these guys can be repurposed for different kinds of projects, and they want to as well. They don't. It's really mind-numbing work to actually send a command and wait, right, a long time for these commands to come back. So there's a human efficiency to the workforce that is a significant expense. As far as feasibility, we didn't go into the project thinking much about that. There have been various government directives over the past few years where at the top
like NASA commissioners have said, we need to deploy more advanced compute. And so a lot of those decisions in the past have come bottom up, right? The engineers making these systems have said, yeah, there's a lot of cool stuff out there and a lot of really advanced compute, but we're going to go with what they call heritage kinds of systems. So systems that they know have been ruggedized, radiation tested. That's actually really important. I've done a lot of radiation testing in building these kinds of systems. And it's another reason why we wanted to work with Qualcomm, because they actually have a history of actually thinking about this. One of their chips was in the health market as well. So ruggedization is really important. But to answer your question, we didn't necessarily go in and thinking a whole lot about feasibility of what you're talking about. We just wanted to know that, hey, even if it was we could work out all this technical stuff, right, with meeting the weight budget, right, the compute budget, non-effective power efficiency. We just wanted to answer certain fundamental questions about if the AI these days, right, is good enough, right, for a lot of these aspects of the mission, that we need very, very direct control over. So it was actually very unreasonable how we started out. Now that we're getting traction, we do have to address some of these questions. So you bring up a good point. I don't have a great answer for you. It started out with an unreasonable goal, and now we're like, oh, but people seem to be interested in this, and we have to start addressing these things. A lot of the aerospace experts we talked to still think we're crazy, or even right, for the reasons you talked about. I will say that if you go to your average space conference these days, there is, and you see, right, there's also there's the directives to advance the compute, but there's also a lot of vendors, right? We chose Qualcomm, but there are a lot of vendors, right, that just cater to government and aerospace that are creating systems for this kind of stuff. So actually, it's not just us being kind of crazy, right? We're seeing stuff happen in the vendor space that are trying to also move this in a direction, getting more advanced compute algorithms in these systems. They've been stuck on these heritage systems for quite a while. Thank you. Yeah, good question. We're crazy. Yeah.
Hi, George. Thank you again for the talk. Just a reminder, my name is Jarvin. Two questions. One I can do really quick. Just for transparency's sake, I know you mentioned that Qualcomm did end up sponsoring this project in general.
Yes.
Was that before or after you guys did your refining of which chips are best to use for this?
They were just really interested, right, in what we were doing and offered their hardware. So they weren't pressuring us to choose them. They were high on our list because they actually have deployed in some of these military aerospace contexts. For that reason, they were also interested. There's definitely an area of like I said, ruggedization. There's a lot of they actually do some good stuff around radiation testing as well. A lot of chip manufacturers are starting to do a lot of radiation testing of their chips. Qualcomm has probably a longer history of doing it for consumer chips. So.
Awesome. And then for a lot of the vast majority of us, actually, we're graduating this year. I'm curious about for people who are interested in getting data science positions or MLE positions, working with edge devices. Do you recommend that they go looking for edge-related positions immediately, or do you think that they should get other experience before that, or what do you think is our into working with edge devices as data scientists, machine learning engineers?
Yeah, so there are a lot of edge conferences that have been happening. There's been a big uptick. They are both online. Like there's the Edge AI Foundation, which I attended in the past week. A lot of these are appearing, they're amplifying. You're in the best place in Silicon Valley for this. They tend to happen, I noticed, down south in San Jose. Not too far away, but there's a lot of conference activity. So I suggest attending one of these, like some of the webinars. Usually they're like multi-day webinars, and then going to some of these events. They also have science fairs. Sorry, not science fairs, but job fairs as well. I expect to see an uptick in the need for AI engineers, for data scientists, for ML engineers. I'm kind of seeing it already. Even in some of the tools that I see for edge hardware, like STM electronics, they make microcontrollers, like for cars and for medical equipment. It's interesting, they have like this tool for doing AI, and they have two paths. If you're an engineer, they give you one path, right, for the highest level easy tools to use to get your model on a device. And then they have a path for data scientists and machine learning people who actually, and they give them more knobs and dials, right? Because you guys know the knobs and dials that you need to adjust, right? Not just to compress the model, right? Like I said, it's not just about compressing the model. At this point, right, you can compress it down to 1 or 2 bits, right? It's what do you lose, right, when you do these aggressive kinds of compression. So you need, right, you need the abilities that you guys have in order to make those assessments and to want to make those assessments. I don't see that changing.
All right, thank you very much.
Yeah, good question.
Hi, thanks again for your talk. My name is Trevor, and I just had a quick question about the agentic flow part of the presentation.
Yeah, a very simple, cute agentic flow that would never be deployed in an actual vehicle. Yeah, go ahead.
Yeah, and maybe you'll probably speak on it a little more, but you showed like that one slide of the footprint, and it like figured out, you know, this is one that we should like ask people for this.
Yeah.
Do you have a fail-safe in the proof of concept where, you know, I imagine a lot of the photos aren't going to be as clear-cut as that, as like a very clear footprint in the sand, you know, that's kind of an easy one, where it's not really sure, because if the fail-safe is just default to call for help, or like how that works, because I imagine a lot of those discoveries are very hard to find in these images.
Right, it can be a very fuzzy boundary.
Yeah.
And so, yeah, like I said, yeah, as you said, right, we wanted to keep it pretty simple. There are a lot of important details that we need to think about when we're talking about real data, right, that you're acquiring. That's why we think we need to actually probably curate real data in a training. But yeah, I think I don't like I'll admit it to you guys, and I know you guys have like talked about this and used it in the projects, but I don't like the current state of model evaluation in the world today, right? And I looked at it, right? It was like, okay, we can use a larger model to judge a smaller model, maybe that's useful. We label a ground truth data set, right? And so now there's a tremendous human burden, and I think that's probably the best use case for what you're talking about, is to tease out that boundary. Is it going to be capable? Arenas, right? We hear of companies that are sort of cheating, right, on the arenas, and we have these standard benchmarks. And I've been doing machine learning, right, since like the early 2000s, when it was like super lame, right? And so, but the model evaluation discipline we had like 15, 20 years ago was a lot better, right, than we have now. Right? No longer are the days where you split your training and then you validation and then you test and you cross-validate, right? You get a good sense of those days are gone. So I don't have a really good answer, right, for doing this. I think at the end of the day, right, we do sort of these vibe checks with experts, and we create a ground truth labeled data set that we're continually evaluating. And I think that's probably the best we can do. Unless something else comes out, maybe you guys know of a better way to evaluate these language models these days. But it's not easy. It's not easy. And we do need to provide certain guarantees. Right? That's important for these missions.
Thank you.
Thank you. Great question. Thank you. Oh, yeah. It's a key to agentic architecture. Probably need a whole lot of.
Okay, thank you. For students who don't know, George was actually my mentor during Kaggle X, and Kaggle X happens every year. So if you guys are interested in participating, please check out the rules for participation. It was a really, really good experience for me, and George continues to do that. So you might get lucky enough to get paired with George again. Yeah, I learned a ton from George, so that's why I invited him. to give a talk. So thank you so much.
Great.
And then
It was okay. You will invite me back?
Yeah, I will invite you again back next year, for sure. So for this agentic flow, was the first idea that you had was to use the agents, or did you first test this with just a prompt and just say, can you do all of these things, and is it relatively fine?
Yeah, it's like a lot of these things. You start out with sort of this idea that's crazy, and you do the simplest thing possible. And so it was just like prompting on getting a cross-modal model, finding one that was pretty small, that fit within like some criteria budget, and just seeing how it would work on various kinds of data. We actually, a lot of the data from these deep space exploration missions is publicly available, right? NASA's a government entity, so they have to actually release a lot of these things. So we tested it on some space images, and it actually worked pretty well. Right? A lot of these images, a lot of them are black and white, but they have geologic structures in detail. This one's more entertaining to show. And plus, we did not find any images with footprints on real Mars. That would have been the discovery of the decade.
Okay, so just to be clear, for the scientific agent, triage agent, exploration, call for help agent, you actually did have just a prompt at first?
Yeah, we just wanted to see what it would do with these these rocks and these geological structures. And we're like, oh wow, this seems to be legit. It's got some science knowledge. And then we needed, right, originally we were thinking it does need to make high-level decisions, right? And that's where we started to add to it, right? Well, it needs to, based on that scientific analysis, make some very important decisions, right, about what to do. So we kind of came up with those two scenarios. And that's where we started to explore the agentic frameworks, right, of which there are like 50 of them now. We stuck with Swarm just because it's been out there longer. In the triage agent, I think if you do like an agentic 101 course, that's like one of the first agents, the agentic RAG example, which is, oh, should I do a vector search query or should I do a SQL query? And that seems to fit with what we were thinking with, all right, a very simple scenario where it needs to make a high level decision. And that's kind of how that sort of evolved.
And then did you end up having like statistics or data to show how much better the agent was performing rather than just a big prompt?
No, we just chose, those were the very first two models that we chose. I wanted to do like a bunch more models. I was just been super impressed with Gemma 3, right? These super small models. I couldn't really find anything that was as good. But to your point, right, we need to do an exhaustive survey, right, of what's out there. Because science, right, is not just about computer vision and doing scientific analysis, right? All sorts of other data, right, that these models need to work with. And some models will be better at others.
Okay. Thank you. My last question is about the experts versus the non-experts.
Yeah.
Did you tell the experts that they were evaluating large language model output?
I think if you clicked on the link there, we put a description that we used. We did a couple surveys. The one I showed you was the second one that was closed. The first survey, but we kept the language. So if you look on there, it will say we're just training AI. We actually say we're using cross-modal models that can understand images. And that's basically the description.
Okay, so the experts then might be aware of the fact that it's created by AI rather than a human. That might bias your responses. The experts might rate them worse because they know that they're made by AI.
Yeah.
Just one thing to know.
No, that's a good thing to tease out. Yeah, you're exactly right. It was just we sort of told them because we thought we were super cool. We said, hey, we're using AI, right? So we put that in the description. So you're right. In a real study, and I think I'm seeing some of these sort of papers that are coming out that compare if you think a human is you're interacting with a human versus if you're interacting with a machine. Yeah, that would be an interesting thing to tease out.
Yeah, recently doctors have done that, and doctors will rate AI better than other doctors, like on average higher, but they don't know that they're rating the AI higher. So, just one thing to think about. Thank you.
Yeah. There's so many biases, right, in these kinds of things, and so being able to think about those biases to quantify them, to come up with a design of experiments where you can quantify them. This is a deeply data science activity. It's not even an AI engineering activity, right? It's a pure AI data science activity. And we can borrow from a large literature of how this is done in healthcare.
Thank you.
Yeah, thank you.
Okay. Thank you so much, George. That was wonderful.
Just kidding.
Oh, she's in. Victoria's in. You're in? Okay, wait. Let's start on this side then.
Oh boy.
No, start this side so they
That
have
side. Ready? All right. It's gonna go down and back.
Yes.
All right. Down and back. So this side, you've got to go. Good, right? All right. Don't let me down. Don't let me down. All right. Here.
I think that's